Okay, so we're moving through 11.2. Now we're going to talk about geometric series, which are a particular flavor of infinite series. I mentioned that we have actually, in fact, already talked about one. And so we'll see how that connects to the broader set of geometric series. But first, let's start with another picture that I think is, it follows in the same spirit as what we did previously, and it's actually a little bit more aesthetically pleasing, maybe. But in this case, we're going to get another fractal. So understand that at some point I'm going to stop drawing, but really it's infinite. So you would have to keep going forever in order to fully represent what is actually, what object we're going to get here. So we're going to start with a cube again, or a square that is 1 unit and 1 unit in its dimensions. So the total combined area right now that we see is going to be a quarter. One. I said a quarter because I was already glancing ahead at what the next step is, which is we're going to quarter the square to 4 smaller squares. And we're going to label just the bottom left corner with its area, 1/4. And then we're going to do that again with the top right square. We're going to quarter that one. So in half and in half again to get 4 equal area squares. Now the area of this new square that we're going to label, which is again going to be in the southwest corner of the new square that we quartered, is going to be a quarter of the previous one. So it's a fourth times a fourth, which gives us 1/16, and so on. So now we'll do it again. And so the next one is going to have an area of 1/64, and again, and again. And eventually, we're just unable to get any smaller than that. And so the key pattern to recognize here is that each time, right, so if we're separating this square into 3 distinct pieces, right, so we have, or 2 really, so we have all the labeled pieces on this diagonal, and then we have these other pieces here, right, so we can call this the A pieces, the B pieces, the C pieces, and so on. And these are the same area as each other, right? But they're also the same area as the one that we labeled with the areas. So really what we're doing is each time we're getting a self-similar pattern where we're splitting the area into thirds, the available area of the square into thirds. So 3/4, we're going to split them into a quarter each, and then the 3/16, we're going to split those into 1/16 each, and so on. And the beautiful part about this is that then this suggests that this equation is true. 1/3 equals the infinite sum from n equals 1 to infinity, 1/4 raised to the n power. Okay, because each term here, right, is 1/4 to the 1 power, 1/4 to the 2nd power, 1/4 to the 3rd power, and so on, right? Of course, what this really means is this infinite series in this form converges to the real number 1/3. But this is just one example of a geometric series, just like having the square is just one example of a geometric series. What we mean generally by geometric series is a sum of the form from n equals 1 to infinity of AR to the n minus 1. And we call that R the common ratio. And then A is the is actually the first term of the series, because if you write it out, term-wise, right? You get a plus ar plus ar squared plus ar cubed, and so on. Or more accurately, right, that this is the sequence of partial sums, a plus ar, a plus ar plus ar squared, a plus ar plus ar squared plus ar cubed. Now, our question naturally is going to be, when does a geometric series converge? Does it depend on A? Does it depend on R? One thing that's important here to note is because A is common to the whole thing, right? A actually doesn't matter. A can be anything at once. A can be as large as you could possibly want, and it doesn't matter. And that's because A can, in theory, be factored out, right? It's not like that's not a hard and fast rule for all series, but we will see a limit law for series that represents that notion of you can factor out, and you can't see my the quotation marks I'm using with my fingers, but we can so to speak factor out that A, and it won't matter. It's R that really matters. So there are three cases. Case one is the degenerate case, which is R equals 1. And I call it degenerate just because it's not interesting, but we should still see it. Okay, so in this case, right, if we plug in 1 for R, we get A times 1 to the n minus 1. And what we actually end up getting is just the infinite series of just A. Because 1 to the any power is just 1, so this ends up looking like A plus A plus A plus A plus A, dot, dot, dot. Okay, so this gives us the partial sum sequence n times A, right? Because each time you're just adding another copy of A. And A can be anything, right? Regardless, this converges to... No, sorry, does not converge. This diverges, I'm sorry. It'll diverge to infinity or negative infinity depending on the sign of A. But that doesn't really matter because it just doesn't converge. So that means R equals 1 is not an interesting case. It diverges. Case 2. We're going to take the absolute value of R to be between 0 and 1. And what is this going to do is, because the magnitude of R is between 0 and 1, and not just R itself, it's going to allow us to account for two possible cases here, which is to say R could be negative too, and that doesn't matter. So here's how we're going to determine our claim. So let me write our claim. So claim, for case 2, the series will converge to A over 1 minus R. Okay? So how? So importantly here, we're going to use the fact that R is going to be, the magnitude is less than 1, so it's absolute value. And we're going to examine the sequence of partial sums, and we're actually going to get an explicit formula for the sequence of partial sums in this case, just like we did in the previous one, but it's actually going to give us something that converges. So S sub n is A plus AR plus AR squared plus dot 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 plus AR to the n minus 1. Okay. One thing that we can start with is we can factor our A. That doesn't matter, right? This is a regular sum now. Okay, this is a finite expression. our usual algebraic intuition works. 1 plus r squared plus dot 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 plus r to the n minus 1. Okay. Now, I'm going to use this cool trick, which is going to, it's basically going to exploit a factorization rule. It's a special factorization rule. It's not commonly covered unless you've taken certain college algebra courses. I'm going to multiply this expression by 1 minus r over 1 minus r. So why am I doing this? Because there's a special factorization. So I'm going to use an aside here that says the binomial 1 minus x to the n equals 1 minus x, whoops, I didn't mean to do that, times 1 plus x squared plus dot 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 plus x to the n minus 1. And of course, in this case, I'm using x because that's what we're used to seeing in polynomials, but really here, then it's r, right? All of which is to say that our numerator, once we multiply in that 1 over r, is going to become a times 1 minus r to the n power all over 1 minus r, okay? So we're using a special factorization, the difference of nth powers. Really, it's a special case of even that special case because 1 to the n power is 1. So this actually is, anyway, I won't belabor the point. The point is, we now have an explicit formula for S of n, and you'll notice that this depends on n exactly in one spot, which is that upper, the numerator has a factor that has an r to the n, and so if we apply our usual limit strategies, we'll see how this works out. So the limit as n goes to infinity of S of n, if it exists, is going to be the limit of, and I'm going to break this up now into two pieces. So if we factor in that a and split it up into two rationals, we get a minus 1 over 1 minus r minus a r to the n over 1 minus r, okay? And the important piece here is, first of all, this is constant in n, okay? So this is constant in n, sorry, not 2n. So the limit isn't going to do anything to that. It's really this piece here that we are going to focus on. And it's the fact that the magnitude of r is less than 1 that allows us to actually find something interesting here, which is a over 1 minus r minus a times the limit as n goes to infinity of r to the n all over 1 minus r. And importantly, this limit, because r is a fraction with absolute value less than 1, it's going to converge to 0. This limit is 0. So we have it. This is a over 1 minus r. Okay, case 3, and you'll see why we had to do case 3 after case 2. That's when the magnitude of r is greater than 1, okay? Notice that S of n has the same form. So we didn't actually use that information about how large r is until the very end. And so the limit as n approaches infinity of r to the n is actually infinite. It could be plus or minus infinity. It doesn't matter. But in any case, so then the sequence of partial sums diverges, and so the sum diverges. Okay, so let's see some examples. Let's go back to the quartering the square. And remember that the expression for that series had just 1 over 4 to the n power, okay? Which, this isn't exactly in the format that we want for a geometric series. You remember that we want it to start at the power of n minus 1. So what might help is if we think about, write out the series and remember that a is the first term, right? So that's a. And then the common ratio is going to be whatever a times r is here. So this is a, and this is a times r, which really means r is 1/4 as well. It really just means we can split this up into 1/4 times 1/4 raised to the n minus 1 power. And once you multiply that in, you'll realize that is literally the exact same thing. And there's almost no point to writing it this way, except having it in a standard form allows us to figure out what the sum converges to, if it does converge, right? So in this case, right, a, again, doesn't matter, but that's a, and this is r. They're the same. And 1/4 has a magnitude, an absolute value less than 1, so the series converges, okay? And what is the limit, right, of the sum? Then we know that I'm just going to write sum equals, but really more accurately we should say the limit of the partial sums is a over 1 minus r, which is 1/4 over 1 minus 1/4, which is 1/4 over 3/4. And then because there are two fractions, one over the other, that have the same denominator, we have 1/3. And that conclusively shows what we set out to show, which is that when we quarter the square, this shaded area adds up to 1/3. Very cool, huh? Okay. One other example that we could see that we've seen before, actually. What happens to this series? So if this, no, let me not write it that way. Does this series converge? If so, to what? Okay. So you might recognize this as this is actually this sum represents the remaining length of the, sorry, not the remaining length. This represents the, okay, I messed it up already. I think, because we're taking out 1/3 and then taking out, yeah. No, it is 2/3. This represents the length that we've removed from the Cantor middle third set. That's more accurately right. Okay, so if this does converge, which I claim that it does, because the common ratio is 2/3, is its absolute value is less than 1, and then we'll have to find the sum. So it'll help if we write this as, in the standard form, as 2/3 times 2/3 to the n minus 1, okay? And so A and R are the same. It's not going to change too much. Like this kind of, was it already in the form that I wanted? Maybe it was. Okay, that was actually unnecessary. Sorry, I got carried away. Because it's already got a power of n minus 1. Anyway, let's just go ahead and do it. All right, so the sum, so we claim, because absolute value of 2/3 is less than 1, the series converges. And the limit of the partial sums is going to be a over 1 minus r, which is, the first term here is 1 over 1 minus 2/3. Which is 1 over 1/3, which is 3. Okay, this this isn't quite representing something related to the Cantor middle third set, because I must have transposed or written wrong one of these series. This is why I was confused. But it does converge, and it converges to 3. So you add up all these 2/3. Yeah, that makes sense. Why would it? It makes no sense that it would add up to. Okay, so converges to 3. All right. Okay, we'll see. One application though. It has to do with decimal representation of numbers. So just as an example, right, we're going to take the repeating decimal number, 0.3 repeating, which is 0.3333, ... and so on. This, by the way, just as an aside, decimal representation, one really funny thing about it is, even though it allows us to represent every number that we can think of as that is a real number, it doesn't do it uniquely. So when we represent, for instance, a repeating decimal number, there is something interesting to be said about the fact that certain numbers, because they are technically series, can be represented more than one way as a decimal number. This is not exactly one of those examples. The example that most people think of is this one. 0.9 repeating is actually equal to 1. Not just approaches 1, not just is very close to 1, but is actually literally the number 1. And the reason for bringing this up at all is because it actually has to do with how they're really at their very core a series and what they converge to. So let's just stick to 0.3 repeating for now and recognize that we can write it as a series as 0.3 plus 0.33 plus 0.333, sorry, not 0.3, 0.03, 0.003 plus 0.0003 plus, and so on, right? Each time splitting it up into basically the digit that we're representing. So this is 3 times a 10th plus 3 times 100th plus 3 times 1,000th and so on. And this is actually what we mean when we say, right, the digit in a decimal representation of a real number, right? There's the tens place, there's the hundredths place, there's the thousandths place. So maybe it's more accurate to represent this as a series from n equals 1 to infinity of 3 times 1 over 10 to the n power. And here's the cool part. Every decimal number can be represented with this. The thing that's changing, though, is sometimes we get a decimal representation that has the same digit every time, right? So this one is a repeating 3. And so rather than having a unique, different expression for the leading coefficient here, or the first term, each time it's going to be slightly different. Like another way of writing this, which is going to be more accurate to the way that we want to show that it's a geometric series and what the sum is 3 times 1/10 times 1/10 to the n minus 1 power. Because the first term really is 0.3, right? So notice that the common ratio is 1/10, which has a magnitude less than 1. So the series converges to 3/10, the first term, 1 minus 1 over 10, which is the ratio, which is 3/10 over 9/10, which is 3/9, which is 1/3. Crazy, huh? Okay. Here's the even more wild thing. And this is, feel free to skip this if you want. It's really not that important. It's just kind of like, it highlights the flaws of how we try to represent math in ways that humans can parse them, particularly decimal representation. So what is 0.9 repeating? It's the same idea, right? So it's actually equal to the sum, the infinite series, n equals 1, of 9/10, right, times 1 over 10 raised to the n minus 1 power. So the only thing that's changing here is the fact that the digit that's repeating is 9 instead of 3. And so that converges to, so the sum is literally equal to 9/10, the first term, over 1 minus 1/10, remember, a over 1 minus r, which is equal to 9/10 over 9/10, which is equal to 1. 0.9 repeating is literally equal to 1. Okay, so in the next video then, we're going to talk about another set of interesting series, particularly the harmonic and telescoping series.